Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So today we're going to look at the square root of a complex number, and this is going to be from our discussion or an initial part of our discussion on operations of complex numbers. And of course in this particular video we're going to look at a specific example which is going to shed light on how we can be able to describe the square root of a complex numbers. And of course in our other videos we're going to look at some of the specific rules, especially the De Moivre theorem and other aspects which we are going to consider whenever we're going to find the roots and powers of complex numbers. So we had said that we can be able to represent a complex number using a phasor z, and this was given of course in terms of a plus b I, whereby we said that a and b are going to form a set of real numbers, whereby I is going to represent a complex and imaginary aspect that is going to be given as the value of the root of -1. So therefore, a and b are going to consist of a set of real numbers given as such. And therefore, we said that from this particular argument, then therefore the concept of a is going to form the real part, and the bi, which is a coefficient of bi, is going to form what we call the imaginary part. And this therefore generally is going to represent what we call a rectangular or a Cartesian or a representation of complex numbers, which we had said from our first case, which we had referred to as a rectangular complex, and sometimes, as we said, this one can as well be referred to as a Cartesian form of complex numbers. And secondly, we said that we can be able to represent complex numbers in terms of a polar form, whereby we said that if the general case for representation of a number can be given as x plus y I, this is going to be referred to as a rectangular form, as I've said. So the second part, we can be able to give it in terms of a polar form, whereby we say that this is given as where r is the modulus, and this is given as r, the cosine of an angle theta, plus I, the sine of theta given as such, and this is going to form a polar form representation of complex numbers. So in this case, we can be able as well to represent a polar form of a complex number, or an expression of a polar form of a complex number that is going to be abbreviated as r, the angle theta, or sometimes we can be able to represent this one in terms of r theta given as such. So from this particular case, then therefore we can be able to derive a way of representing this root of or the square root of a complex number by having this particular expression. We can use either of these, but we can have this first one, implying that this particular representation is a derivation or a derivative of a number that was given as a square of r given as such, and then therefore this is going to represent an angle of half theta given as such. So this is going to be a deduction, or we're going to deduce that this basically representation of this complex number was a result of the square of the root of these two specific numbers, and I have these particular angles which are going to give us the second aspect of theta given as such. So therefore, suppose we have two representations for different values of r and theta, we can be able to have a general case whereby we're going to have it given as the product of these two moduli, and then we're going to have the addition of these specific angles, which are going to be respective angles for theta for r1 and theta for r2 given as such. So this is going to imply that this was a derivation of the modulus of the first angle and theta, and the product of the second angle and theta 2 given as such. And from these two specific conclusions, and therefore we can be able to deduce that z basically can be given as a representation of r, and then the first angle, half of the first angle, and then the representation of r, and then this is going to be half the second angle given as such. So therefore we can be able to generally give the value for z given as r, and then this is going to be half the angle and the square of that. So this is going to represent this particular argument that we had given basically from our first. Let's give this one as equation 1, and this is going to be equation 2. So this basically argument is going to be a conclusion from equation 1, whereby we say that we can be able to represent this particular representation for the polar system as the root of this specific squares of r, and then the half of these angles, which are going to give us a sum of this specific case. So in this particular case, then therefore we can as well argue that this particular representation was as a result of this specific the root of the square of this specific value and this representation, and this is going to give us a general theorem for representation of square roots of complex numbers. Therefore we can be able to say that for us to find the root of a complex number, we can be able to assume that this particular complex number is another complex number having the modulus that is equal to the square of the roots of a given modulus, and the argument that is a half that of a given argument given from this particular expression. So to simplify that, perhaps I'm going to give it in terms of an example whereby we are going to, of course, try to find the root or the square root of a complex number given as the face of z is equivalent to, so these are just given as that one. So this is equivalent to 36 and then 24 degrees given as such, whereby this is going to be the modulus and this is going to be the argument given as such. So if we are required to find the square root of this specific number, then therefore we are going to use this specific argument, or this first one, whereby we're going to find it as the root of this particular complex number is given as the root over r, which is a modulus, and then the angle theta over 2 given as such. So therefore we can be able to find this specific root by doing a substitution, whereby we're going to find it as the root of 36, which is the modulus, and then we're going to have it as a half the angle, which is given as 24 degrees divided by 2 given as such. So this is going to give us the value of 6, and then the angle 12, which is going to form the root of a complex number which we have specifically given as 36, and then the angle of 24 given as such. So therefore this is the general format that we're going to use in trying to find the roots of complex numbers. And if we are going to do more examples, of course these are going to assist us in trying to find a more of course meaning in trying to use this specific approach in finding roots of complex numbers. So that is it for now, guys. Catch us in our next video. God bless.